Coral reefs are entering a phase of collapse. A system once stable is now under accelerating stress. This is not just an ecological crisis, it is a climate signal and a systems warning. In this chapter, we explore the threats, the tipping points, and the pathways to survival. Coral reefs are deeply linked to the Earth's climate system. The oceans absorb most of the planet's heat, buffering global temperatures, but they also absorb carbon dioxide, changing ocean chemistry. This leads to acidification and rising thermal stress. Together, these forces are reshaping reef ecosystems. The chemistry of the ocean is beginning to shift. As carbon dioxide dissolves in seawater, it forms carbonic acid. This reduces the availability of carbonate, the building block of coral skeletons. Calcification slows, structures weaken. What appears invisible is fundamentally changing the reef. Coral reefs are more than ecosystems. They are indicators of ocean health. When reefs begin to fail, it signals deeper systemic stress. Changes in temperature, chemistry, and biology are reflected first in coral systems. If coral reefs fail, the ocean system itself is under threat. The scale of change is already visible. Since 2009, approximately 14% of the world's coral reefs have been lost. This is not a gradual decline, it is a systemic shift, a signal that reef resilience is weakening and that the window for action is narrowing. Coral bleaching is a stress response. When ocean temperatures rise, corals expel the algae that feed them. Without this partnership, they lose both color and energy. What remains is a weakened, starving organism. Bleaching is not just whitening, it is the beginning of collapse. Marine heat waves are becoming more frequent and lasting longer. These prolonged temperature spikes push coral systems beyond their limits. Recovery windows are shrinking, while stress events are intensifying. What was once rare is becoming the new normal, and reefs are struggling to adapt. Ocean acidification is weakening coral from within. As carbon dioxide increases, the ocean becomes more acidic. This reduces the ability of corals to build strong calcium skeletons. Growth slows, structures become fragile. A reef that cannot build cannot survive. Local pressures are accelerating reef decline. Pollution from land carries sediments, nutrients, and waste into coastal waters. This clouds the water, blocks sunlight, and disrupts photosynthesis. The reef begins to suffocate. What starts on land ends in the ocean. Excess nutrients are changing reef ecosystems. This process, called eutrophication, fuels rapid algal growth. Algae spread faster than corals and begin to dominate. They block light and compete for space. Gradually, the reef shifts from coral to algae. Direct human activity is physically damaging reefs. Bottom trawling tears through fragile structures. Anchors crush coral formations. Unmanaged tourism adds further stress. These are slow-growing systems. Damage that takes seconds can take decades to recover. Coral reefs are approaching critical thresholds. At just 1.5 degrees of warming, 70 to 90% of reefs are at risk. At 2 degrees, nearly all reefs could be lost. These are not distant projections. They are tipping points, beyond which recovery becomes unlikely. The Great Barrier Reef offers a clear warning. Repeated bleaching events have affected vast stretches of the reef. Each event reduces resilience and slows recovery. What was once a stable system is now cycling through stress. A global icon now reflects a global crisis. When coral reefs decline, the effects ripple outward. Fish lose habitat. Food webs begin to unravel. Coastal protection weakens, and livelihoods are affected. This is not a single loss. It is an ecological cascade moving through the entire ocean system. Recovery is possible, but only under the right conditions. If stress is reduced, corals can regain their symbiotic algae, growth can resume, and ecosystems can rebuild. But recovery takes time, and repeated stress events can prevent it altogether. Science is now working to actively restore reefs. Corals are grown in nurseries under controlled conditions and then transplanted back into damaged ecosystems. These efforts can accelerate recovery, but they cannot replace the need to reduce underlying stress. Coral reefs are connected across vast ocean distances. Tiny coral larvae travel with ocean currents, settling far from where they began. This genetic exchange links reefs across regions. A healthy reef can help restore another. One reef can save another. The path forward requires decisive action. Global emissions must be reduced to limit ocean warming. Water quality must improve to reduce local stress, and critical reef systems must be protected. Without coordinated action, recovery will not be possible. Protection must be strategic, not just widespread. We must focus on reefs that show resilience to climate stress and on regions that supply coral larvae to others. These are the sources of future recovery. Protecting the right reefs can safeguard entire systems. Saving coral reefs requires global coordination. Policy must align with science, and both must engage local communities. Conservation cannot be isolated. It must operate across scales, from local action to international frameworks. Only integrated effort can protect these systems. Coral reefs are not just ecosystems. They are living infrastructure. They support biodiversity, stabilize coastlines, and influence climate systems. When reefs are healthy, oceans are more resilient. Protecting reefs is protecting the foundations of ocean stability. The future of coral reefs depends on the choices we make today. Protect reefs, and we stabilize ocean systems. Lose reefs, and we risk systemic collapse. This is not just an environmental decision. It is a choice about the future of life in the ocean. Coral reefs are not just ecosystems. They are the foundation of life in the ocean. They sustain biodiversity, support livelihoods, and stabilize coastal systems. What happens to reefs shapes the future of the oceans. Protect them, and we protect life itself.